All right, hello everyone. Welcome to episode 12 of Games with Go, where we will be learning how to do bilinear interpolation, also known as bilinear filtering, from scratch, and then we'll see how to do it, and alpha blending using SDL instead of doing it ourselves. So one quick thing before we begin is a quick fix from the last couple episodes. If you go back to the noise project, inside where we parallelize Go, we have this line right here, and on stream, I typed divide by height, and that should be width. So if you were here for the noise stream, fix that up, and you'll be good to go. All right, so let's go back to our balloons program. So last episode, we were able to load up 3 balloons from a file, 3 images from a file that had alpha information, and and draw them with alpha blending. And before we do bilinear filtering, I wanted to just make a few things a little nicer. So right now, this is what our program looks like. And this is not so good for seeing how the alpha blending is going because we've got 2 balloons on top of each other. So I'm just going to go in here. This is where we're loading the balloons, our load balloons function. And here we create a balloon texture. And I'm going to make the position a function of the index. So we're just going to offset each balloon a little bit to the right and down. Like that. So that gives us a little bit of a better view. We can see the green behind the blue. When the green comes back, we can see it behind the red as well. Or see the red behind the green. All right. And the other thing we can do to make this look a lot cooler really quick, if you remember before, we used our noise package in Pong. So if you go back to Pong, and find the rescale and draw function. And we're going to reuse this code. You can just start copying rescale and draw, get clamp, get the gradient functions, and these two linear interpolation functions. Let's copy those and bring them into our balloons program. Do a paste, and then we renamed color to RGBA. So we need to fix that up. Here, here, here. Couple more. Okay, I think that's everything. And let's go up to the top and let's import our noise package. Let's see, how did we do it in Pong? Do we need to give it the full path? Yeah. So we need to give it our full path. Okay, now it's found it. Now let's go ahead in our main function. So we want to make some noise. We want to make FBM, fractal Brownian motion. Let's see, what type or what parameters do we want to give it? So let's give it a frequency, 0.009, linearity of 0.5, gain of 3, and 3 octaves. And we want this to be the width of the window. We're going to use this to make a background for our balloons. That'll look pretty nice. All right, then we want to make a gradient for it. And everyone, you can do whatever gradient you think will look nice. I'm going to do something that'll look like clouds. So this will be blue. We'll go do a gradient from blue to white. So maxing out all 3 colors will get you white. And then we're going to get some cloud pixels. By passing the noise. Oh, we need to get our noise here. Cloud noise. Oh, also our min and max. So make noise returns multiple values so that we know our min and max. So give it min and max, and then give it our cloud gradient. And width and height. All right, what are we unhappy about here? Too many values. Oh, we're probably not doing alpha. Okay. All right, then we need a cloud texture so we can draw. And that'll be we'll need our cloud pixels and width, height, pitch. What else do we have in our textures? So position. That'll just be 0, 0 because we're going to draw it up at the top. Oh, this should be here. We'll start in the upper left-hand corner and draw over the whole screen. Okay. Then instead of doing a clear, I think we can just draw our cloud textures. We don't need to use draw alpha because cloud texture is going to be the first thing we draw. So we don't have to worry about alpha, so it'll be faster. All right. Now we have a nice cloudy background. Okay. So what I'd like to do eventually is have these balloons not just be able to move up and down, left and right, but also have them float backwards and forwards. And to simulate that, we'll need to make the images bigger or smaller. We need to be able to scale them. So the naive way to scale is pretty simple. You basically, if you're going to make the image bigger, you just draw each pixel multiple times according to the scale. And if you're going to make the image smaller, you just skip pixels. So let's give that a try so we can see what it looks like. This will be a function that operates on textures. And we'll call it scaled, draw scaled. And then we'll, whoa, mouse. First thing we want to do, this will need to also take, we'll need 2 floats. So we'll need, let's see, scale X and scale Y. So that would let us, if we want to, scale the image differently on the X and Y axes. So we could like stretch something this way or squish it that way. So we need to figure out what the new width is going to be when we apply the scale. So that'll be the texture's width times the scale factor. Right, so if we pass in a, I wasn't that happy. Oh, it's just because we haven't used it. The new height. Will be the texture's height times the scale Y factor. And then I'm going to just pre-compute the pitch here. And then we'll do our usual for y loop. But this time we're going to do for y equals 0 and y is less than the new height, not the texture height. So this could be bigger or smaller. And then we want to compute the floating point y value, right? Because we're going to be wanting to draw pixels that don't actually exist in the original texture. So let's 32. So let's do that. So we'll call this call it fy, and that'll be equal to the actual the integer y value that we want in our new texture divided by the new height. So we're kind of getting the percentage along the y-axis that we are on the new texture. Times the height of the old texture, right? So we're getting the y value of the new texture in terms of the size of the old texture. And then we'll want the integer approximation of that. So that when we pick a pixel from the original texture to make our scaled version, we can use the truncated version of this float. And then we want to get a coordinate to draw this on the screen. So that'll be fy times scale y plus the texture's x position. Okay, that's fine, that's fine. And then we can compute the screen index. So this will be the index into the pixels array. Or the starting screen index. Whoa. Okay, so we're going to taking these current screen Y coordinates times the pitch plus the x position of the texture. This will be like that. All right, that'll be our starting index. And we'll do x from 0 to the new width. And we'll do the same thing. We'll do the floating point value of x, new width, and fxi will be truncated f of x. And we'll also get the screen x, which will be the int of gx times scale x plus and this should be y up here. All right. Then one thing we want to do is we want to check if the screen x and y coordinates are actually on the screen. So you could be drawing a balloon that goes off the screen partially, and we don't want to try to draw the pixels that aren't going to be there. So x needs to be greater than or equal to 0. Needs to be less than the width. Same for y. Less than the wind height. All right, then we'll get our fxi. We can pre-multiply this times 4. Fx. All right, now we're going to fill in pixels. So we're going to set our screen pixels at the screen index that we computed by the texture pixels at the, we'll use the integer approximations we've computed. So we'll do GYI times the pitch of the texture width, not double times, plus GXI 4. And we'll increment the screen index, and we'll do this for green and blue. So plus 1 to get to the green, plus 2 to get to the blue. And we're just going to skipping alpha. For now. Okay, so I'm going to give this a try. If anyone has questions about all of this, let me know. So we'll now make each balloon or each texture have a scale. And when we load our balloons, we will give them a scale. We'll say let's do 1 plus I. Okay, so the first balloon will be normal scale, then they'll get bigger and bigger. And then when we draw our balloons, we'll do it with draw scale instead of draw alpha. We'll do it by scale. X and Y scale will be the same. All right. So it works. One thing you notice as we get really big, the image gets more and more pixelated. Right? We can see the individual pixels because all we've done is just drawn the pixel a whole bunch of times. And so what bilinear interpolation is a technique to kind of smooth this out, to like take an educated guess at what the pixels should be that we don't actually have information for. So let's draw it out. So the situation is we're wanting to say we're scaling up a texture. And these blue dots represent pixels that actually exist in the original texture. But we want to scale up the image. So there's going to be all these pixels that we want to draw that don't exist. We don't have any information for them. But we want to make a clever approximation. All right, so say we wanted to draw this pixel here. What color should it be? We know the color of this pixel, this pixel, this pixel, this pixel, but not this one. So what bilinear interpolation is, it's pretty simple. It's just linear interpolation, which we're familiar with from previous episodes, done twice. So the first step is you do a linear interpolation from this pixel to this pixel, right at the point above the one you want. Right? So you give it whatever percentage you need to get it right there. So you figure out what color that is in between these two with the linear interpolation. And then you do the same thing with these two pixels. You do a linear interpolation for them at the percentage that gets you right below the pixel you want, and you get that color. So now you've got two new colors, and you do a final bilinear or linear interpolation between these two new ones at the percentage that gets you exactly on the pixel, and then that's your pixel color. So if you do that, you get something that will be a little bit smoother because these pixels aren't just repeating the colors that are next to them, but they're doing a combination of all four pixels that they're surrounded by at the appropriate ratios. So let's give it a try and see what we get. So we'll take our simple draw scaled function. We'll just copy and paste this. That'll be our template. But now we need to do a lot of interpolating. So once we get in here, let's simplify this for now. We're going to need to get the 4 pixels around the pixel we want. So we're going to call those, they're going to be C00, C01, C10, and C11. That's going to be our convention to refer to those 4 pixels that we actually have info for. So we're going to get indexes for each of them. Like this. So this is our top left pixel. Then we're going to just do subtraction to go all around. interpolation. All right, so this gets us the indexes for the pixels all around our pixel that we want. So Tx is going to be the percentage between the top two pixels that we want. So we're basically getting the difference between the exact floating point value and the truncated one. And then we can do the same thing for y. I'm going to say ty is equal to fy minus the truncated. All right, that gets us the other percentage we need. Then we're going to do multiple interpolations. So we're going to do a couple helper functions. We'll do one that does linear interpolation on floats. So we can call it AB percent float 32, and it will return a float 32. Basic linear interpolation. And then we're going to do the bilinear interpolation, which will take C00, C10, C01, C11, and our TX and our TY, all float 32s, returning a float 32. So we're going to do the, remember in the picture we did the 1, 2, 3 linear interpolations. So that's what we're going to do here. We'll do the linear interpolation of the linear interpolation from C0 to C10 by TX. And then C01, C11 to TX again. And then that final linear interpolation by TY. TY being this percentage vertically that we need to go. All right. Let's call this bilinear scaled. Okay. So to save on tons of typing here, we'll actually use a loop in here. So we'll do from I is equal to 0, I is less than 4, I plus plus. So this is just to get us the R, G, B, and alpha without having to repeat ourselves 4 times. I'm going to actually reverse these. Okay. All right. Okay, yeah, that should be the colors. So this was the indexes to all the pixels that we know. This will be the actual colors. So we'll set the screen index. So So we'll do this, or we'll do the bilinear interpolation. So then we do bilinear interpolation of C00, C10, C01, C1, px, ty. And we need to convert this into uint8, or a byte. Then increment the screen index. All right, I think that's it. Oh, so now we need to go down here though and tell it to use our new bilinear draw on, yeah, on the balloons. All right. So now you can see it's been smoothed out a little bit. It's not perfect. And there are more computationally expensive ways to do this that can look a little better. But we're doing it. Now things look a little bit better as you scale them up. So that's bilinear interpolation done in software by hand. But you notice we haven't done alpha blending yet. So if we added alpha blending, that would be even more work we have to do computationally each frame. And if you look down here at milliseconds per frame, you can see on my computer we're taking 19, 20, 22 milliseconds per frame. So that's already dropping us below 60 frames per second. And we haven't done alpha blending yet. And we're just drawing three sprites. It's not a lot of sprites. If we added more sprites, this would slow down even more. So this is getting way too slow. Now, if we were really clever, we could probably find a few micro optimizations. Are we back? I think we're back. Are we back? Someone in chat confirm or deny? All right, cool. So we could potentially do some micro optimizations in here. We could mess with this code to make it a little faster. But we really need to be a lot faster. We want to be able to do, hundreds of balloons, not just 3. We ought to be able to get, 200 frames per second with something that's just 2D. So what we're seeing here is basically the reason why 3D cards were invented, why GPUs were invented. And basically what a GPU is it is a chip that has hundreds or even thousands, usually thousands today, of cores on it. And they could take a function like this, and instead of having one core operating on 1 pixel at a time, all 1,000 cores are operating on 1,000 pixels at a time. So they're massively faster, especially for this kind of math operation where you're doing the same thing on every single pixel. And fortunately for us, SDL has functions built in to do things like alpha blending and bilinear scale and bilinear filtering, and they will use the GPU if you tell it to. And interestingly, if you tell SDL2 not to use a GPU, it will not do bilinear scaling, right? So it's not just that we're not clever enough or that Go isn't fast enough to do this in real time. Even the people who wrote SDL and C decided this was not not worthwhile to do in software. All right, so what we're going to do now is we're going to refactor our balloons. Now that we've kind of learned how this rendering works, we're going to use SDL to do it for us, which will then use our GPUs if we have one. So let's give that a try. Let's make a new directory, call it balloons2. And let's just copy everything. Well, let's copy our source from balloons into balloons2. Let's copy the balloons as well. And the credits. And let's rename this. You can hit F2 when it's highlighted to rename. Balloons2.go. Okay, first thing we're going to do is we'll get rid of the texture, our own texture, because we're going to use SDL textures from now on. We're going to have something similar. We're going to keep a balloon struct, but it's just going to have a position and a scale. It is not going to have any pixels in it, but it will have an SDL texture, so pointer to an SDL texture. And so texture is the type that SDL uses for its textures. And so we have to use SDL period to refer to it, because it's in the SDL package. Okay, so now we're going to want to delete our old software functions from this copy of balloons. No more draw scaled, no more draw bilinear scaled, no more blurp or flurp. Tangent in chat asks why star SDL? Because we are going to keep a pointer to a texture rather than copying the texture around. We don't need multiple copies of the texture if we're putting it in different data structures. Like you can imagine 10 balloons that all share the red texture, so they don't need to have copies of it, just a pointer. And texture.draw we'll get rid of, draw alpha we'll get rid of. Okay, so something we're going to need is a way to take pixels and make an SDL texture out of them. So let's call that pixels to texture. And whenever we do something for creating textures, we need a copy of an SDL renderer. So we're already making one of those. If you remember back from SDL2 setup, we're making a renderer. And in fact, the way we've been doing all of our software rendering so far is we do actually make one texture, and we're just drawing all of our stuff into that one texture. So now we're going to have lots of textures we're going to draw. So we'll take some pixels, and we'll take a width and a height, which are integers, and we'll return a pointer to an SDL texture. All right, so to get a texture, we call render.createTexture, and we give it a pixel format. And something that is a little bit weird is the pixel format I'm choosing is ABGR8888. And we've actually been ordering our bytes by red, green, blue, alpha, not alpha, blue, green, or 8. So the SDL constant for this is backwards like this because of Indianness. On some CPUs, bytes go in one order, and in others they go the reverse. That's why it's like that. So you just have to remember that the SDL pixel formats basically are backwards from the way you're actually going to be filling in your bytes. And then you give it the kind of access your texture needs. So if you're going to be modifying your textures often, you want to make it streaming. If you aren't, you're going to make it static. We'll leave ours as streaming just in case we need it. Let's close that balloon. And it needs a width and height as well. But it has to be an int 32, so we got to cast. All right. And as always, check the error. We'll panic if we get one. And then to set a block of pixels into a texture, you can call update. If you can provide a rectangle if you want to set only a sub portion of the texture, but we want to set the whole thing, so you just pass nil in that case. And what's our pitch? Our pitch is width times 4. So pitch, again, is how many bytes are in a single line of the texture. So we are 4 bytes per pixel and width pixels. So pitch is 4. Okay. Now this is going to return, we're going to go to load balloons, and it's going to return an array of balloons instead of textures now. And this will just be balloons, spelled properly. Okay, so we're still going to open all of our files. We're still going to decode the PNGs. And we're still going to fill up our balloon pixels. But then we're going to get our texture by saying create, what do we call it? Pixel to texture. Oh, we'll need a renderer in here now, so that's good to know. Renderer. Renderer, pass in our pixels, and our width, and our height. That's all it needs. And then our balloons will be a balloon is a texture, a position, and a scale. So that'll be texture, leave our position the way it is, and the scale will just be 1. No, we'll make it just like we had before, 1 plus I. Should be balloon pixels. Okay. What's this upset about? Misspelled balloon again. Every time. All right, so now load balloons is going to return our balloon structure, which will contain SDL textures. Our noise can stay the same. Okay, our cloud texture now is going to be pixels to texture. Pass it the renderer. Pass our cloud pixels. And then width and height. When width, when height. Okay, so now our cloud texture is an SDL texture. This will just be balloons, not balloon textures. And we got to pass our renderer now. Okay, so now how do we draw an SDL texture? So one way you can do that is you can use the renderer. You say renderer.copy. and just give it a texture. And then if you're just going to draw the whole thing, you can pass nil to both source and destination. So you're drawing the entire source to the entire destination. So that's going to draw our cloud texture. We also want to draw our balloons. These are now balloons. So we kind of just want to say balloon.draw at this point. But I think we'll need to pass it a renderer. So let's assume that we do. Okay, so how do we draw our balloons? Okay, so in order to get the scaling, we are going to have to use, so we're still going to use renderer.copy. And we're going to pass it our balloons texture. The source will stay nil, but our destination rectangle will change. So if we give it a bigger destination rectangle, the whole texture is going to get bigger. If we give it a smaller destination rectangle, the whole texture will get made smaller, get scaled down. So we got to figure out what that rectangle is going to be. So first, let's figure out the new width, right? Because our balloon has a scale. So let's get our new width. So our starting width times the scale, our new height. And then let's make our position for balloons represent the center of the balloon. That's going to be handy later. So we'll take the x minus the new width divided by 2. So what this is doing is if we want to make the x and y represent the center of the balloon, then we want to start drawing a little up and to the left, right? So this is our balloon texture. This is where x and y is. When we actually start drawing, we want to go over here, right, to the left half the width, and then up half the height to start drawing there. Then we're going to make our rectangle, which is just a struct, which has an x and a y and a width and a height. Pretty simple. And we pass that rect. What is this I'm happy about? Okay, so let's make our balloon also have a width and height, because it is hard to get a width and height out of the texture. So now our load balloon is going to have to add that information. Easy fix. Balloon.scale. All right. This warning that you'll get, you can ignore. It's okay to do this. All right, so we got a new draw function that uses SDL's built-in facilities to draw things scaled. This needs the renderer. That should just be balloons, balloons, balloons. All right, let's see what happens. Oh wait, that's the old balloons. Nothing. Why did we get nothing? Nothing's pretty bad. Oh, okay. So we are still trying to use our old software renderer here. Right, this is what took our old pixels array that we were drawing into, updated the one texture we had, and then copied that texture to the renderer. So we don't want to do that anymore. And in fact, we don't even need that pixels array anymore. So we'll delete that. That would just be wasted memory. Let's try again. All right, cool. We got some balloons. But we don't look like we have any bilinear filtering, and we don't look like we have any alpha blending. And we need to adjust our positions since we're drawing at the center of the screen now. So let's fix these things. Let's adjust our positions a bit. Let's not make these quite so big either. So that'll just make them not quite as huge. Okay, so first for alpha blending, we have to tell SDL that we want to do that. And how do we do that? Okay. So the alpha blending is done on a per texture basis. So what we need to do is once we've created a texture that we want to do alpha blending with, we need to set the blend mode. So there's different blend modes you can do. And you can see those if you do SDL.blend mode. You see there's add, blend, mod, none. And you can experiment with these. The one that is similar to what we were doing before is blend mode blend. That's sort of normal alpha blending. And then this can return an error. I believe if you're on hardware that doesn't support alpha blending, which might be nearly impossible now, you could get an error. So if you wanted to handle this, you could probably just ignore it. You just wouldn't have that blend mode set. But this is how you'd find out if this didn't work. Let's give this a try. All right. Pretty good. We can now see that we've got alpha blending going on, but we still don't have bilinear filtering. So the way you set that is with a global setting. And we can set that right after we create our renderer, I think. So you can call SDL.setHint. And there's different hints you can give it. And one of them is hint renderer scale quality. Right, so that's the quality it's going to use when you scale textures smaller and bigger. And if you give it 1, that's going to do bilinear filtering, similar to what we were doing. Anytime you scale a texture. And they call it hint because it does not necessarily mean SDL will do this. It's just going to try. Let's give it a try. All right, and you can see it's much, much smoother than it was before. And the other fascinating thing you can see is over here at milliseconds per frame. We're usually at 0, sometimes occasionally 0.5 milliseconds per frame. That is the magic of GPUs. And then something fun you can try is you can go over here to where we created the renderer. Remember, one of our settings was renderer accelerated. You can tell instead, select renderer software. Let's see what happens. So now you can see not only are we losing our bilinear interpolation, but we're also getting 4 or 5 milliseconds per frame just from doing the alpha blending. So someone in chat is asking what kind of GPU I have. I have an NVIDIA 1070, so it's a really good one. But I believe even if you just have an integrated Intel GPU, you'll still get really fast performance with this kind of stuff because it's pretty simple. If anyone's tried it and wants to say what milliseconds per frame they get on an integrated GPU, I'd be curious. All right, that wraps up what I wanted to get done tonight. But we still have a few minutes, so if anyone has any questions, concerns, criticisms, or comments about this episode or any previous episodes, feel free to let me know in chat. So NameGuy101 asks why SDL software renderer got 4 to 5 milliseconds while ours was doing 20. One reason is that ours was still doing, we were getting 20 when we were doing bilinear interpolation. SDL just gives up on bilinear interpolation when you do software. It doesn't do it at all because they know it's going to be too fast. Now you absolutely could with, if you wrote a bilinear interpolation function in C, you could make it quite a bit faster than we did, but it still wouldn't be fast enough for any reasonable use. So here we're back to SDL software renderer, and if you look, it might be hard to see on stream, but it's not doing any bilinear interpolation. There's big blocky pixels here. If you try it on your own, you'll see it pretty clearly. So it's just giving up. I'm sure also that their alpha blending is a little bit more efficient than ours. Again, you could do SIMD intrinsics in C to make those faster by quite a bit. And you can also do SIMD intrinsics in Go to some extent, but you have to use Go assembly, which maybe in a future stream, we'll get into how to do that. I really like SIMD instructions. I think they're a lot of fun, but they're kind of painful to use in anything but C. Chat asks, does SDL render accelerated cause SDL to use OpenGL? I don't think so. I'm pretty sure not. But you can use OpenGL along with SDL. But I think SDL is just talking to the GPU directly. But I don't know. That's a good question. They might be leveraging OpenGL to some extent. There's probably some platform that doesn't have OpenGL that SDL supports and it still works, but I'm not sure. Tangent asks, can Go use the GPU? Yes, absolutely. I mean, in effect, we are using the GPU right now. Or I guess I should say Go can use the GPU just as well as any other language can. The way you use the GPU is you write programs in a shader language. Um, if you're using OpenGL, it's called GLSL. If you're using DirectX, it's called HLSL. And those get compiled down into GPU assembly. And so if you're using Go, you would just load up a shader file or type the shader into a string, and then Go could send that shader to the GPU using OpenGL or DirectX or whatever. And then the GPU runs that code. Okay, NameGuy 101 says in chat that you can set Sdl.Set Log Mode and set it to log mode verbose, and it'll tell you what render it's using, whether it's Direct3D or OpenGL. And you can force it to do one or other and create window. So we're not saying anything, so I'm not sure what it's defaulting to. But I'll play around with set log and set log mode and see sometime. A final point about using the GPU. Some languages are able to develop libraries where you can write, for instance, you can write C# code that gets compiled into GLSL shader language. I don't know if anyone's done that with Go. I don't really think it's a good idea either. It's better just to write shaders and shader languages. All right, any other questions before we go? All right, thanks everyone for tuning in. What we're going to do next episode is, now that we're kind of using SDL the way it's intended, we're going to kind of turn this balloon thing into a simple 2D game. We're going to have these balloons just floating around, and then we'll be able to pop them, make them explode. I think we'll make them like hydrogen-filled balloons. And that'll let us learn how to do mouse input as well as touch input. We'll support touch screens. If you touch the balloon, you can pop it. And maybe also sounds and animations. So we'll learn how to do an animation effect and play sounds when you pop the balloons. So I don't know how many episodes that'll take, but we'll see. All right. Good night, everybody.